à l'Université technique de Darmstadt. À vous la parole, cher Oliver, pour cette conférence conclusive. Si votre micro ne fonctionne pas.
Merci beaucoup et merci pour l'invitation. Je suis désolé, je vais présenter en anglais maintenant. My French is just not good enough. So, welcome everybody. My name is Oliver Tessmann and I'm heading the Digital Design Unit in the Department of Architecture at the Technical University in Darmstadt. And I would like to talk about multi-sites modular constructions, and I will explain during the lecture what I mean by that. And what I would like to show is how we work in research, but also together with students to develop new ideas that revolve around computational design, digital fabrication, robotics, and how these topics might contribute a little bit to, hopefully a different way of how we design and materialize architecture. And the motivation for that, I think, became very clear during that day. But before I start talking, I would like to show a movie on the second slide. And we need a little bit more sound. Next slide, please. We do that old school. I say next slide, like when we had real slides, because the remote doesn't work from here, unfortunately, with my computer. In, I think, in 2020, there was an exhibition in the Stockholm Center for Architecture and Design called Flying Panels, How Concrete Panels Changed the World. And you can see here an image from the 1960s from the Soviet Union. And in that time, there was a housing crisis after World War II, and prefab concrete was seen as, the emerging technology that was supposed to solve that problem. And it was really regarded as high-tech. If you look at other images of that time, can you go back one more time, sorry? You see prefab concrete next to the rockets that the Soviet Union was shooting into space. So it was really high-tech. It was also, there's also a societal message here. We see men and women working together on a construction site. And we see these panels flying in. They, of course, hang on cranes, but they are somewhere in the background. So the flying panels as a positive technological vision of the future that is supposed to solve societal problems as well. That's Soviet Union, but in the next slide, we see how that prefab concrete systems, of course, did not stay in East Europe alone. They can be found all over the planet. And Erik Stenberg, a researcher from the KTH in Stockholm, documents that with the Million program, which is a program from the 1960s in Sweden with the ambition to build 1 million apartments within 1 decade, which they managed due to the use of prefab concrete. Next. This is where I come from. That's the architecture building in Darmstadt on the Lichtwiese campus. And it was finished in 1968. And the first thing that they did when they built the campus was setting up a concrete factory, a prefab concrete factory on the site to produce all the elements for a couple of buildings that were built in that era. And if we look at the next slide, then we can see that what is often associated with repetitive and monotonous architecture can, of course, provide great spaces. And we are very happy to use these internal lobby and the different galleries every day. You also see that it's a hybrid. It's a bit of prefab and quite a bit of on-site concrete as well. Next. This is a building from 2019, an award-winning building, and it won the awards because of the ambition to create low-cost but high-quality architectural housing in Berlin. However, if we look at the construction, then we see that there's almost zero innovation in prefab concrete elements within the last 60 years, right? I think on the next slide, I'm comparing the two, So this is what we got 1968, and this is what Berlin got 2019. So we really have to think of how to change the way we build. Next. The flying panels became kind of a banal reality, right? This is exactly what happens on construction sites. But as we all know, flying is very CO2 intensive. That's why on the next slide we see, or we think, that architecture elements should maybe not fly so much, but rather wobble and roll and move in a different way. And that's why we let them interact with dancers, and you saw that in the initial video, and the story behind that will come towards the end of the lecture. Next. I think that quote appeared in French this afternoon already. Concrete, the most destructive material on earth, is what The Guardian writes in 2019. And of course, that refers to the high CO2 emissions that originate from producing cement. It is, of course, only one side of the story, because we all know that concrete is a kind of genius material that allowed a lot of humans on the planet to have a decent home. So, next slide. Most probably, we will not replace everything that we built with concrete today by using timber. And also Karen Srivener from the EPFL says that this would not be a good idea because we will most probably not be able to plant as much forest than we would need to replace concrete. And then we have a lot of underground structures that, of course, cannot be done with timber. We have another problem, and that's shown here. That's a university building in Frankfurt that was blasted in 2014. Next to it is the famous Senckenberg Museum, is one of the most important collections of animals and insects and stuff. And they did a good job in not letting the tower fall onto Senckenberg Museum. But it was an event. You see on the background the thousands of people looking at it. So what is almost like an art performance with a certain aesthetics, of course, is at the same time a terrible destruction of building elements, of architecture, of all the time and energy and design and engineering intelligence that went into that building. And, well, what falls down here will then be downcycled and used for road constructions, as we know. This becomes even more absurd when we look at the next slide. So, 1973, that thing was built. 2014, it was blasted away. And that's what we got in 2018. And you see on the Senckenberg Museum thingy in the front, this is the same perspective. The picture was taken from the same perspective. And seeing this sequence of images, I'm convinced that we need to fundamentally reassess the way we build, but even more profoundly, we need to reassess the conceptual and theoretical framework of durability and permanence and linear material flows in architecture. The concepts heavily rely on the Vitruvian idea of firmitas, in which mass and solidity are meant to form an eternal architecture. And this notion of permanence of buildings is deeply woven into the disciplinary thinking and into the value system of architecture. It also, or at the same time, prevents an integration of more circular strategies within the design, use, and reuse of buildings and their components. At the same time, we witness an extremely volatile real estate market where high turnover rates guarantee profits, and permanence is absolutely not a concept there. It's more a take, make, waste approach that fosters material consumptions and the production of demolition waste. So linear thinking forms the basis of how we design architecture, and it is encapsulated in our design thinking, in our design tools, and of course in the construction techniques. The business models, building codes, and the legal framework are still geared towards linear building elements. Luckily, we see things starting to move, and well, events like this one today push this movement forwards. Current attempts for more circularity mostly focus on recycling at the material level. At present, a circular economy on the building element level is confronted with challenges that result from harvesting products not designed for reuse, leading to work-intensive on-site mining. And we saw that already in the talk from the EPFL this afternoon. In our research, we aim at fundamentally rethinking the notion of permanence in architecture by proposing a process of continuous transformation of the built environment. Here, permanence is not established within a single building, but rather through building elements that endure as reused components in potentially numerous buildings, sites, and functions. In reference to the title of this event today, this would lead to modular constructions that are not off or on site, but would become multi-site modular constructions. Permanence is achieved through continuous transformation. And at the Digital Design Unit, we cannot solve the problem alone, but we constantly search for ways how digital technologies can contribute to this paradigm shift. Next. And if you want to reuse what's there, if you want to urban mine, and if you want to do that in a digital process, first thing you have to do is you have to digitize what's there. You have to 3D scan what's there. This is what we did with our architecture building and with our wonderful and creative and engaged architecture students that got the surveying guys over to bring their equipment and scan the building. You see elements flashing in blue. This is what the students speculate would happen when data-driven or artificial intelligence-driven technologies would help to identify elements in point clouds and kind of generate geometric or even building information models out of that. We also work with students by looking at rubble, at waste. And then we use first scanning, but then also algorithms to describe these random and complex geometries. First describe them, and then we look for ways of how we could maybe put them together in new ways to build something new. And if there are gaps in between, next slide, then maybe we can combine what is already there with 3D printed elements. Here, these orange adapters that work a little bit like when you, how's that called in English? When you get something for your teeth, right? If you go to the dentist, he's scanning and then he's printing something that perfectly fits in there. So with these adapters, we can connect to what is there, and in this case, it's a concept, so to say. It's an idea that we put into an arc to exemplify that, building with existing context could be supported by 3D printing. Next. We scan, we get an idea of the building stock, of the material stock of existing buildings, and then we, of course, need algorithms that take those elements, that take what's in the stock, and then reconfigure it to create novel designs. Next. So what are the elements that you can pick in the stock to build what used to be a column in the building and could become an element of a bridge? This is, again, student work, Zhang Peng Chen, who speculates of how that could happen. Next. And if you want to reuse an element, you might need a little bit of subtractive action as well to put it in a format that it fits within the newly designed overall construction. And again, student work that prototypes this process. Next. And then you might need to click to start the movie. Yes. And then you assemble, which is quite a mess if you try to do that with dry joint with dry joint connections. So if you don't glue stuff together, but you really have the ambition of make it a reversible assembly. This is what you see here, and which led to the bridge that you see on the next slide. And we go on. So all these ideas lead to what we call a real digital process chain. We start with something that is physical, that is real, and then we put that into a digital system. And then we do something new with it. And what started as a work with students with a lot of speculation was then further developed into a research project with a German title, Fertigteil 2.0. In English, it's not so elegant, Precast Concrete Components 2.0. It looks at exactly the process chain you just saw, and we teamed up with the University of Braunschweig, Professor Harald Kloft, who's a structural engineer, but who also is equipped with a large robotic lab for additive manufacturing of concrete, but also for putting sawing blades on robots to cut elements. We had Faro in there as a company for 3D scanning. Our colleagues from the Design and Sustainable Building Group that looks at life cycle assessment, and then a startup that tries to organize the logistics in a digital way to do that. And this is the diagram, and you saw all the steps. We need to digitize what's there. We then work with digital models to kind of upgrade these precast concrete components, and then what is planned digitally happens with the physical objects. And then after that, urban mining and refurbishment and upgrading process, these elements can be used for novel constructions. Next. And yeah, again, the process, so 3D scanning of elements, and we go to the next slide. And then from the point cloud that you see here, next slide, to identifying regions in that point cloud that might belong to certain elements, next, which then step by step lead to a more refined geometric description. And then here we plan to, or identified the areas where we would like to cut buildings into pieces to gain these elements. Next, with the aim to, harvest new elements. We plan to do that in a building in Braunschweig, and we encountered one problem that you get when you want to work with the existing elements. Buildings have to be demolished or disassembled. Unfortunately, this was planned to be done with this building in Braunschweig, but it never happened within the time where we did the research project. So we had to find another source for building elements, and you see them on the next slide. This is an old bridge, and that is on the Campus Lichtwiese in Darmstadt. So it's part of this prefab system that's even called Darmstädter System. And it was meant to be torn down, or it was meant to be demolished. And then we said, hey, stop, can we have a few of these elements, please? And they gave us this. And then we had a partner with very big saws, as you can see here. And he was letting these columns fly again, which I think is very nice. And then they were put on a truck and brought to Braunschweig. Next. Ah, yeah. So 1968, they are arriving, and then 2022, they are flying out again to be brought to Braunschweig to be upgraded into Fertigteile 2.0. Next. So again, scanning the single piece, and next. Then giving every single piece a marker. Here it's an RFID tag. Next. and then all the data that we gained of an element goes into a database, and we kind of developed a clickable dummy for an app that we thought would be helpful for people to get metadata, get information of these elements into a database and create a digital twin which can then constantly be fed with novel information. Next. So these are then the pieces digitized. Next. And this is the lab in Braunschweig, and you can see there's a large gantry system with 2 hanging robots and 1 with a big sawing blade. Next. And we used this to make cuts. This is a cut being made for a 3D printed column, where you can see that cutting helps to create precise surfaces to join other elements to the printed column. Next. And we used the system, of course, to get rid of the stuff that we wanted to get rid of to really refurbish and upgrade it. We put some threaded bars in to test whether this would be possible systems to create reversible connections. Next. And then looked at different ways of how these elements could be put together to form something new. Next. And then ended up developing a kind of novel connection detail. On the left, you see the system from the 1960s. And on the right, you see these grayish metal sleeves that are bolted together and which allow to assemble, disassemble, and reassemble. Next. So this is how the old new piece looks, the Fertigteil 2.0. Next. And we produced a couple of them. Next. And yeah, envisioned them to be part of a larger system that could become a multi-story building again. Next. And here you can see the construction of a demonstrator. Next. Which is then screwed together. Next. To form this heroically lit piece to show what we did with the old pieces and how that could become something new. Let's jump over that. We try to put all the data into the system. Next. So it goes into a database, and from that database we kind of get a component database. Next. And that's what's interesting. Now we connect what's there as a, go back please. We connect what's there at stock, what we harvested through the urban mining process and what we upgraded into new elements. And then we link that to designs. So what we said is we don't want the architect to worry about thinking of what's there on the courtyard waiting for me, but we say, you give us a 3D model, and then we do the matchmaking. Yeah, it's a bit of a Tinder for building components. We look what the architect wants to build, and then we see how these elements could fit in there. Yeah, and this was the algorithmic part that we developed at the DDU to bring these two worlds together. Next. Yeah. As I said, the sustainability group at Darmstadt looked at an LCA analysis, and of course, reusing concrete makes a lot of sense. If you click one more time, there's a diagram that looks very similar in values to the EPFL presentation today. So the blue bar, that's the production of concrete raw materials, and if you take that out of the equation, then you achieve quite remarkable results. So it makes sense it makes even sense if you have to transport them for a little bit. Maybe Darmstadt, Braunschweig, 300, 400 kilometers is a bit too far, so we need local markets. But I think comparing these bars on the left, you see the reuse, in the middle it's recycling concrete, but that's a German way of looking at it, because in Germany you're only allowed to have a small fraction of recycled concrete to mix with new concrete, and then compared to new conventional concrete, that's on the right-hand side. But what if we design new elements instead of refurbishing old ones? Could we design systems that from the very beginning are or can be assembled and disassembled and reassembled? This is what we are looking at in the next project. Next slide. It's called tactile robotic assembly, and on one hand it looks at the elements, and on the other hand it looks at how we can assemble and disassemble and reassemble these elements through the means of robots, and ideally these robots act as autonomous as possible, so that something that is very labor intensive can be automated, can happen autonomous. And if it happens autonomous because these robots are equipped with sensors, so they kind of perceive the environment, they are driven by AI, or they are trained through reinforcement learning, then they can do their job on their own. But autonomous robots also means that they are really prepared for interacting with humans on a construction site, because to do that you have to perceive if a human interferes in your region. You have to make decisions, and only autonomous robots make decisions. Next. The building component that we work with is borrowed from a Taiwanese researcher called Chi, and he developed what he calls an SL block. It's 8 cubes, 4 of them form an S, 4 of them form an L, and together they are an SL block. Next. And what's interesting about the SL block is it can interlock with the second SL block in 6 different ways. We see that on the next slide. So if you put them together in different ways, you achieve different effects. You can build linear, you can build diagonal, you can build spiraling, you can build as a massive volume. And it's all happening through interlocking. There's no need for glue or mortar or any adhesives, so it can be disassembled. It relies on friction though, which is a problem for robotic assembly. Next. Yeah, here you see different grammars or different rules of how they can be put together. Next. And we heard about the mid-20th century industrialization of architecture, serial production. We heard a bit about non-standard or parametric systems where every element is a unique part that fits only in one position in a construction. Here we have something else. We have a repetitive element, but it can be composed or combined and aggregated with others of these elements to form different combinations, different aggregations. So variety is not achieved by individual components, but it's more about the combinatorics of those elements. And we consider them as really one-to-one scale, very small elements, and we were wondering, could they become larger construction elements that might even interact with existing constructions. And if you want to do something like this, it makes a lot of sense to automatize the assembly of this, because, of course, that's a very labor-intensive process. Next. And if the geometry is the common denominator, then maybe what we can differentiate is the material. And we can say that there are regions that take care of carrying loads. There are regions that are there for insulation. But they have something in common. They can interlock with each other so that an entire building could be a multi-material aggregation in which every single piece is a single material which can be easily reused in different contexts. Next. Yeah, and then of course, assembly, disassembly, and the reassembly in something new. That's what I said earlier. So the permanence is not anymore in the building, but the permanence is in the piece, in the element that travels through space and time from one building to the next. Next. We started creating a setup. There's a material feeding system that gives the robot the element. There's a robot that builds, and that's a blind and stupid robot, and a robot controlled by architects. We later, and I show that in a minute, teamed up with computer scientists to make that more smart. But we started building, and you can see that on the next slide. The robot needs a bit of support structure, here shown in red, to then place the elements. And then there's this human slave appearing here and then feeding the feeder. That's, we ignored automatizing that. That will be the next step. And then we said, it doesn't make sense that we as architects program the robot. We as architects pre-program every single step of how these elements are put together. We need to have a robot that autonomously puts these things together without us telling them the trajectory of movement, the place where to put that in. He needs to figure out that by himself. And this is what our friends and colleagues from the intelligent autonomous system groups from Professor Jan Peters developed here. What you see in the gripper, these lights, that is a so-called visual tactile sensor. There's a silicon pad that is a little bit like skin, and behind that silicon pad there's a camera, and when the robot grabs something, the camera sees how that pad deforms, and then they use all the algorithms and the development power of visual computing that was developed for autonomous driving and other applications to interpret this deformation of the silicon so that they can identify the surfaces, they can identify whether an object slips in the gripper, they can have an understanding of the weight of that element, and of course, they also, or the robot also recognizes when there's a collision or when there's very high friction during the assembly. And if there's too high friction, then, and this is what you see in the video, the robot stops the assembly process, goes away, and then tries to approach from a different angle. So it's not us telling go from A to B, but it's more like there's a piece in your hand and there's one line, try to put them together and find the best way how to do that. And that's, for us, the first step to have the whole assembly process as an autonomous one. Next. So there are different ways and different sensors to use in such a process. We saw the visual tactile one in the gripper. Here you see a system where the joints of the robot are equipped with torque sensors that then recognize collisions, frictions, and forces that let the robot do the assembly process in a different way. Next. we jump over that. Next. And we wanted to test the process of first designing with computational means an SL block aggregation that makes use of the different ways of putting that together to form a structure. And then we elementarized this structure, and the single elements were then aggregated with the robot. And then on the next slide, you see first pieces, elements of that structure. Next. And these elements were then put together into the overall demonstrator. Next. And you might need to start that video again. And that assembly process is completely different from a robotic assembly that was really done by a team of researchers and students putting that thing together. Next. So this is our test demonstrator for the whole process of assembly and also of designing with these repetitive elements. Next. I forgot what I wanted to say. I have that in my notes, and I expected to have them here. So we just jump to the next one. Yeah. Now we come back to what we saw in the beginning. So when you watched the movie, you saw people interacting with elements that were put together, that were joined, dry joined, that started to interlock. And then they moved away. And the reason why these large elements could be moved so easily is that they are hollow. And the reason why they are hollow is shown, I think, in the next slide. And that is another video that needs to be started. We are researching a technique of concrete casting which is borrowed from the plastic industry. It's called rotomolding. If you have a kayak, canoe, or a plastic tank, then it's probably made like this. So there's a formwork, and you put very little material in the formwork, and then you rotate the formwork, and the liquid material distributes along the surface of the formwork. Concrete doesn't like to cure under movements, but we had some material experts that developed a recipe that does that. And what's interesting here is that a formwork is needed to define a certain shape that you want to achieve, and it has to withstand the hydrostatic pressure of the liquid concrete. Now, the more liquid concrete you have, the higher is the hydrostatic pressure. And if you fill in just a little bit of concrete, then that pressure goes down. And what you saw as the formwork, or what you see here as a formwork, is just a latex balloon for 50 euro cent, which then is pulled and stressed into this kind of nodal geometry. And the double curvature of that geometry gives enough strength for this super thin membrane to act as a formwork system. And that is Sami Medezade, you see here, who is researching exactly that topic in his PhD. Next. So you get lightweight concrete that you can carry. Next. And you get hollow elements. And it's a bit of an additive manufacturing process, because you start with a super thin layer, and once that is hardened, you add another one and another one and another one. And of course, our long-term goal would be to differentiate this wall thickness according to what's needed structurally, and then let that reflect by the movement pattern of a robot that gently shakes the object. We are not there yet, but we are working on that. We built installations where these things become nodal connectors in space frames. Next. And again, we used the creativity and energy of students to explore what's possible with the system. Next. They built new machines. Next. And here you can see this two-axis rotational movement that is needed to distribute the material. Next. And a couple of elements, columns, slabs, modular elements that could potentially become hollow building structures, building components, which we then also try to group into different categories. Next. Next. Yeah, just examples. Next. All produced with latex as formwork. Next. Next. And then we scaled that up together with an industry partner using a little bit of a bigger robot that can carry larger elements. But again, you see it's a 1 meter element with concrete in it, and just in this case, a silicon membrane that acts as a formwork. Next. That led to this kind of twisted elementarized column. And then we speculated again what could be done with this, and this was an inspiration. If you place the center of mass in a certain way, then you can do amazing things, as we can see here. Yeah? And we thought if he can do that, we can do that with our hollow elements as well. Next. So we explored with students how to design elements that move and rotate and have a kind of counterintuitive center of mass, somewhere where you wouldn't expect it. So it's like these toys that are stable in certain positions where you wouldn't expect them to be. Next. And then combining that with the idea of interlocking again, you can suddenly compose elements just by rotating them, creating assembly sequences that lead to these kind of compositions where, yeah, just through a certain sequence of movement, these things come together, interlock, are piggybacked by each other and form a larger structure. Next. Another beautiful project of students where the movement kind of controls the interlocking. Next. Next. And of course, always the question of what could that aesthetically mean for architecture. Next. So movement and rolling, rotation becomes a means of assembly. Next. Here exemplified by two elements that are choreographed together, and you can see here on the back side that they are hollow. Next. And with these premises, we started designing elements that could roll in different positions, could be assembled, reassembled, so that, again, one piece can be used in different ways, in different configurations. Next. And this was then further developed into an installation that we were allowed to show in an exhibition at the Dutch Design Week last year in Eindhoven, where the TU Eindhoven organized an exhibition called Robots That Build. So we designed a series of elements. Yeah, you can, that should run as a movie. You can see a little bit of the making of. We developed computational tools that simulate this behavior of elements with a particular center of mass. We looked at the rotoforming production processes with a group of students, and then they first designed small-scale models in the studio, and then we scaled that up for the installation. And so this is where we left the digital world, and it became quite a bit of crafting, mixing the material, pouring that into the formwork. And formwork that is open because we could control the direction of the rotoforming here. And then the robot did his job to distribute the material along the formwork. This is a styrofoam formwork, as you can see, so it was not possible to do that scale with the membranes. Next. And this is what came out of it, a series of elements. And we then teamed up with these dancers and choreographers from a Berlin-based group called Tanzpool. And they came and kind of invented on the fly a choreography that tries to generate interactions between humans and objects. And this is the last movie. And I read here, together with the choreographers from the Berlin-based studio Tanzpool, we wanted to explore the interrelationship of choreography and architecture. What happens when you can dance with architectural elements? What if seemingly massive pieces move and rock at the touch of your hand? The massive-looking but lightweight hollow elements are designed as discrete elements that join together but never permanently. With their dry joint interlocking connection details, they are meant to be rolled, wobbled, and rocked by one person without heavy lifting equipment. They can be assembled, disassembled, and reassembled into changing spatial configurations. The performance not only speculates about a more circular approach in architecture and construction, with pieces that will become reusable for future buildings, they will also offer constant dynamic recalibration of architectural elements and the human bodies that partner with them in a novel choreography. The mutually dependent relationship opens up the possibility to enter into ever new forms of interaction between spatial configuration and human bodies, blurring the lines between human, the maker, and inanimate object, and instead offering animate concrete bodies in motion. Inspired by dance theorist Rudolf Laban, who regarded movement as a forming force for living architecture, Tanzpool developed a choreography for both people and concrete pieces. Dancers are exploring the counterintuitive kinetic behavior of the objects, which move unexpectedly due to their surprising and invisible mass distribution that prompts them to move like tumbling toys. Animate Concrete speculates about prefab elements that become parts rolling and wobbling from one building to the next to form multi-site modular constructions. Thank you.
Thank you so much, Oliver. Et merci à toutes et à tous pour votre attention, y compris jusque dans ces heures tardives. Il faut dire que c'était captivant. On se retrouve demain. En fait, Eva, je ne sais pas quels sont les messages à passer, moi. On se retrouve demain. Stéphane, voilà, on se retrouve demain à 9h. C'est ça. Moi, je vous laisserai entre les mains de mon confrère Arnaud Paillard qui prendra ma relève, étant malheureusement retenu ailleurs, mais peu vous importe. Et donc, je vous souhaite une excellente soirée, une excellente fin de colloque.